Modern scientific simulations generate massive, high-resolution data, making storage a major challenge. Implicit neural representations address this challenge by compressing them into compact neural models for efficient reconstruction and visualization. Most existing INR-based approaches in scientific visualization use deterministic models that output only values, without quantifying uncertainty or model confidence. When the original raw data is unavailable due to its large size and storage constraints, we cannot directly compute reconstruction error. In such cases, uncertainty quantification becomes essential to assess the reliability of the model's predictions. There are two types of uncertainty: epistemic uncertainty, which reflects model uncertainty, and aleatoric uncertainty, which captures inherent noise in the data. So far, most existing approaches focus mainly on epistemic uncertainty, while data-level uncertainty remains largely unexplored. One of the most widely used approaches for uncertainty quantification is deep ensembles. It provides strong uncertainty estimates but require training multiple models, making them computationally expensive. Therefore, we propose REV-INR, Regularized Evidential Implicit Neural Representation, a single model framework. To the best of our knowledge, this is the first work that quantifies and studies both model-level and data-level uncertainty estimates using a single INR, and demonstrates their interpretation, usability, and applicability in INR-driven volume visualization tasks. REV-INR builds upon a residual INR with a minimal architectural modification, augmenting the final decoder layer with 4 output neurons. These neurons predict the scalar data value along with 3 additional higher-order distribution parameters for uncertainty quantification, using an evidential learning scheme. By placing a Gaussian prior on the unknown mean and an inverse gamma prior on the unknown variance, the network learns a normal inverse gamma distribution at each coordinate. Using the learned NIG parameters, we compute the predicted scalar value along with its associated aleatoric uncertainty, which captures data-level noise, and epistemic uncertainty, which reflects model uncertainty, at each grid point in a single forward pass. We first optimize mean-squared error to ensure strong scalar value reconstruction. Then, we introduce an evidential loss that aligns the predicted normal inverse gamma distribution with a low uncertainty target using KL divergence, while penalizing overconfident predictions through an evidence regularizer. To make uncertainty interpretable, we proposed 2 regularization terms. Epistemic uncertainty is encouraged to correlate with prediction error, and aleatoric uncertainty is aligned with local gradient magnitude to reflect inherent data variation. We train the model in 2 phases, first with MSE for stability, and then with all loss components, ensuring both high reconstruction quality and reliable uncertainty estimates. To compare REV-INR with existing single model-based approaches, we developed 2 additional uncertainty-aware INRs. The first, referred to as MCD-INR, is based on the Monte Carlo dropout approach. Since conventional MCD-INR only estimates epistemic uncertainty, we extend MCD-INR to also capture data uncertainty. The second model is adapted from RMDSRN, which is also designed to predict only epistemic uncertainty. We build a new INR, consisting of a shared encoder and multiple decoders, similar to RMDSRN, to predict both epistemic and aleatoric uncertainties and refer to this new regularized model as RMD-INR. In enhanced MCD-INR we apply dropout only at the last residual block to simulate a partial Bayesian network without degrading reconstruction quality. During inference, we perform multiple stochastic forward passes. The mean prediction gives the scalar value, variance across passes gives epistemic uncertainty, and the predicted variance provides aleatoric uncertainty. To enable this, we add 1 additional output neuron so the model predicts both mean and variance, and train it using Gaussian negative log likelihood combined with MSE. Regularized multi-decoder INR uses a shared encoder with multiple decoder heads, each predicting both mean and variance. The average prediction gives the scalar value and aleatoric uncertainty, while variance across decoders provides epistemic uncertainty. It is trained using MSE, Gaussian NLL, and an additional KL regularization term to align epistemic uncertainty with prediction error. Results. First, we demonstrate how uncertainty improves isosurface extraction. When extracting isosurfaces using only the predicted mean, we observe structural inaccuracies, including broken connections and missing thin structures, even when reconstruction PSNR is high. In contrast, uncertainty-aware extraction using level crossing probability allows us to visualize the most probable isosurface, Across datasets such as Teardrop and Vortex, REV-INR consistently produces the most accurate and crisp LCP visualizations. RMDINR often overestimates structures, leading to spatial spreading, while MCDINR frequently fails to recover thin connections. Even deterministic INRs, despite achieving comparable PSNR, generate incorrect topologies. These results highlight that uncertainty is essential for reliable structural visualization. Next, we evaluate reconstruction quality through direct volume rendering. On datasets such as combustion, REV-INR better preserves fine-scale structures, including complex flame patterns, and for datasets such as foot it preserves bone joint details. Quantitatively, REV-INR achieves the best PSNR among uncertainty-aware INRs and consistently outperforms MCDINR and RMDINR in PSNR, SSIM, and LPIPS metrics. This confirms that incorporating uncertainty does not compromise reconstruction fidelity. For epistemic uncertainty, we compare predicted EU with actual error fields. REV-INR shows the strongest spatial alignment and highest correlation, indicating well-calibrated model uncertainty. We compare O with local data variance and interpolation-based error introduced during downsampling and upsampling. REV-INR consistently shows the highest spatial overlap and correlation with both local variance and interpolation error, indicating meaningful data-level uncertainty estimation. Finally, we compare REV-INR with state-of-the-art compression techniques such as TTHRESH and ZFP. REV-INR preserves intricate isosurface structures more accurately and achieves the best compression ratio versus PSNR trade-off. Our results show that even when deterministic INRs achieve high PSNR, they can produce structurally incorrect isosurfaces. This highlights that global reconstruction metrics alone are not sufficient for reliable visualization. When raw data is unavailable, uncertainty becomes essential for identifying unreliable regions. REV-INR provides calibrated epistemic and aleatoric uncertainty within a single forward pass, enabling trustworthy and interpretable INR-driven visualization. This work has been accepted for presentation at the IEEE Pacific Visualization Conference and will appear in the conference proceedings. Further details can be found in the preprint version of this paper.